Okay. All right. So thank you, everyone, for being here and giving me this opportunity to talk about quantum computing at AWS. In particular, I will be talking about Amazon Bracket. Before I go ahead, let me make sure you can still hear me. If you can, respond with an okay, yes, thumbs up on Zoom, that would be fantastic. Okay, perfect. All right. So hello, I'm Prajesh Gupta, and I am a quantum applied scientist at Amazon Web Services. My job is basically to work with customers and partners and help them get on board with Amazon Bracket, help them run a small POC or to solve any problem that they might be interested in. And so my job would be to handhold them to their journey on Amazon Bracket, work with them on finding the right solution, right algorithm to solve their problems, and so on. Yeah. So in this talk, I have the following agenda. First, I would like to set up lab environment because I would like this talk to be more interactive. So feel free to ask questions either in the chat or unmute yourself and ask questions, and I will try to answer them as much as I can. And if I cannot answer them, I will make sure to come back to it via email or something. Okay. So first, I'll set up the lab environment. It will be through Workshop Studio. I'll be going over that in a minute. Then I'll be talking about getting started with quantum computing at Amazon Bracket, which basically what we are doing in terms of quantum computing at AWS. And I will give you a little rundown of what Amazon Bracket service looks like in AWS Cloud. Then I will show you a lab demo, how to run tasks on simulators and QPUs. And we'll see if there are any QPUs available today, we'll be able to take advantage of that as well. Then I'll give you a technical introduction of what is called Amazon Bracket hybrid jobs. So hybrid jobs is kind of popular these days because most of the computers, as I will be explaining here, are small, and the algorithms that needs to be run, they have to be in hybrid mode. Hybrid, that is like a tandem between classical and quantum computing. And then I will show you how to run a hybrid classical quantum algorithm on the lab. And then we'll take a little break and reconvene to talk about solving optimization problems with QAOA, that is quantum approximate optimization algorithm with Amazon Bracket hybrid jobs. And then at the end, we'll do a wrap-up Q&A and survey. So once again, if you have any questions, just feel free to speak up, and we will. I'll try to answer them. Okay.
We'll monitor the chat, so if something
Sure.
comes up there, we can amplify it.
Okay, perfect. I also have the chat window open here. So, all right. First thing first, access to the workshop environments. So if you have the link with you, you can just click on that, or if you don't, there is the link is up here. You can type it in, and when you type it in, you'll need to enter the access code, right? And if you already have the link on the Zoom, you'll not need to do the access code. So let me. I'll need to exit.
Oh, I just dropped the link in.
Okay, perfect. All right. So let's talk about what we're doing in terms of quantum computing at AWS. So quantum computing, as you might have heard of, it's a completely new paradigm of doing computing, which is fundamentally different from the traditional computing, because in quantum computing, one uses the laws of quantum physics to devise new hardware that encodes information in terms of qubits, right? And the idea is that quantum computing, it can solve problems which are extremely difficult for the classical computers to solve, because of quantum computing being able to encode and process information in a completely different way. Can you still see my screen on Zoom? Okay, perfect. Okay, so it leverages the intricate laws of microscopic world to perform computation in novel ways. It's a new paradigm to speed up solutions to hard problems. And the idea is that when we have a full-fledged quantum computing working, the improvement in performance will not be linear; it will be exponential. That's the idea. and then one will be able to solve like hard problems, such as in scientific and in business world and engineering world, to to surpass the current capacity of even supercomputers and the largest HPCs. However, building such a device is quite challenging. It's hard, and not only building the device, but what one has to do, one has to rethink all the algorithms from scratch, because the way information is processed in quantum computing is fundamentally different from the classical computing. So one faces challenges first in building a quantum hardware, then devising new algorithms which can efficiently process information and make use of these quantum computers. So in the past 10 to 15 years, what we have been able to achieve is what is called noisy intermediate scale quantum devices. So these devices, in short, NISQ devices are short devices with like a few hundreds qubits at max, but these qubits are noisy. They are very prone to error, right? So they cannot perform the full-fledged computation of quantum computing. But the idea is that even though it's very error prone, maybe one will be able to work with what is called hybrid algorithms and use them in some capacity to solve interesting problem. So that's what is the most lot of research going on today in terms of hybrid quantum and classical computing. Okay, so the potential of quantum computing is it's quite disruptive in many areas. For example, computational chemistry, where one will be able to simulating molecules and trying to come up with new materials is quite a challenging problem. It is quite computationally hard. Even for biggest supercomputers, there are some limitations. And the idea is that with quantum computing, those limitations can be surpassed, and we may be able to devise new materials and so on and so forth. Then comes optimization. So optimization is like ubiquitous. It's everywhere. So quantum computers are when they are designed and they are the optimization problems lend themselves quite naturally on quantum computers, as we will see today that even with the current limited technology of quantum devices, we can solve some optimization problems in limited capacity using the currently available hardwares as well. However, to harness the full potential of quantum computing, one needs to have what is called fault-tolerant quantum computation, which requires hundreds and thousands of high-quality qubits, which is much beyond what we currently have. But the idea is that the future is promising, and the current advancement at the forefront of quantum computing is also promising. That maybe in 10 to 15 years, we may be able to have a fault-tolerant quantum computer, which will definitely be more than sufficient to beat the current, the biggest supercomputers that we have. So quantum computing eras, if we review on x-axis here on this plot, I have number of qubits. So the higher the number of qubits, the better it is. And on y-axis, that's the error rate, that is quality of the qubit. So lower on the y-axis, the lower you go on y-axis, the better it is. So that means the end goal of devising or building a quantum hardware would be a lot of like millions and billions of millions and millions of qubits that are the error rate is very low. So that is this region 3. That is what the end goal is. So far, in last 10 years or so, we have been able to explore this region 1, the pink one, where either we had very few qubits of large, like a good error rate, or a couple of hundreds of qubits with error rate not being so good. So the pathway is to go from region 1 to region 3. And if you remember the recent experiment, quantum supremacy, quote unquote, experiment from Google, that lies somewhere at the interface of region 1 and 2 here. So what about region 1, region 2? So region 2 is where the near-term applications come in. So in the next 3 to 5 years or even 10 years, that's where the most of the devices are going to lie. And the idea is that to use these devices in tandem with the current classical computation technology we have to try to get some kind of quantum advantage. And I will show you a pathway today how we can achieve that in coming time. Okay, so quantum computing at AWS. So AWS, the quantum technology can be divided into 5 pillars that we have up here. The first center, that is AWS Center for Quantum Computing, it is directed towards, working on trying to find out, better error correction codes, trying to find ways to build fault-tolerant quantum devices, and so on and so forth. So that is dedicated to research. Then we have AWS Center for Quantum Networking. So quantum networking, the scientists and members over there, they are working on, developing communication technologies empowered by quantum mechanics. Then we have AWS Partner Network, that is community of various labs and startup companies and so on who are interested in quantum computing to work, and they support each other, and that's the community of Partner Network. Then at the end, we have Quantum Solutions Lab. So Quantum Solution Lab is more like a consulting firm within AWS, and they work with national labs, universities, industries, all sorts of clients and customers to work to find out state-of-the-art quantum and classical solutions to various problems, right? So that's what Quantum Solution Lab is. At the end, I would like to talk about Amazon Bracket. So Amazon Bracket will be the focus of this talk today. So Amazon Bracket is basically the fully managed quantum computer service offered by AWS. Okay. So before we go ahead, let's just check on the account setup. Yeah, so it is still working. So we will have to come back to that. Okay, so moving on to Amazon Bracket, it's a fully managed service that makes it easy for the users to use, to explore quantum computing. So using Amazon Bracket, what can do is first you can build your algorithms, build your programs locally on your computer using what is called Amazon Bracket SDK. Second, you can test those algorithms either using the local simulators on your local laptop or using high performance simulators available online through AWS Cloud. And I will be showing you in detail what these local simulators and high performance simulators mean and what they can do and so on and so forth. Third, you can, through Amazon Bracket, you have access to many quantum hardware that I will be also talking about, where you can run your codes and get some results. And at the end, perform analysis. That one of the power, like the merits of using Amazon Bracket is that you can use all different services that AWS has to offer in tandem with Amazon Bracket to analyze your algorithms, results, and monitor the performance of your algorithms and programs in real time. Before I go ahead, are there any questions? Okay, all right. So let me introduce you to the architecture of Amazon Bracket. So in this diagram up here, you see this bigger box that is AWS Cloud. So Amazon Bracket is a service within AWS Cloud, right? So Amazon Bracket can interact with many different services, like for example, Amazon CloudWatch for monitoring the state of your job submission and so on. Then for notifications, you can use Amazon Event Bridge. So if, for example, if you have submitted a task or a job to either simulators or quantum computers, it can send notifications to your email and to your phone as text message to let you know the status of your job submission. Then you can store results and your data sets using Amazon S3 bucket, that is for simple storage. And then for permissions and data protection, you can use other services as well. The Amazon bracket itself, within the cloud, it's basically based on classical compute, right? So, which has managed simulators to simulate different kind of quantum circuits, and also a capacity for hybrid algorithms where you can, initiate a job instance that can, use efficiently the classical and quantum resources to employ a hybrid quantum classical algorithm. If you see, I mean, the quantum hardware that is not part of AWS cloud, right? Because there is a reason for that. Because the current quantum hardware that we have, they are provided by third-party vendors. For example, you might have heard of Rigetti, IonQ, Quera, and Oxford Quantum Circuit. So they are all located around the world. For example, Rigetti's hardware is somewhere on the West Coast in Berkeley. IonQ is in Maryland. Quera's device is in Boston, and Oxford Quantum Circuit device is in London. So they are not part of AWS cloud. However, they are connected with AWS cloud with a safe and secure network. So Amazon Bracket has priority access to those quantum hardware for you to be able to run your code, right? And then as a user, you'll be able to interact with Amazon Bracket via different methods. First is managed notebooks, which is what we are going to look at today. In my demo, I will show you how you can use managed notebooks to access the services of Amazon Bracket. And then there is local IDE. So local IDE, you can use your favorite IDE to, write your own script on your local computer and then submit that to Amazon Bracket, to run your jobs. Then there is Amazon Bracket console. So the console basically is another way of interacting with the Amazon Bracket to check your job status, see different kind of announcement, and so on and so forth. So that's that. Okay. So talking about available quantum hardware, currently we have 4 different kinds of hardware available. I'll show you more detail of these hardware when we look at the AWS console. But to quickly mention, like we have 2 devices from IonQ. There's Harmony and Aria. So Harmony device is 11 qubit device. That's an older one. And Aria device is a 25 qubit device. So Aria device is special in the sense that it has capability of error mitigation. Rigetti device is a 79 qubit device. It's a superconducting QPU. And device from Oxford Quantum Circuit is again a superconducting qubit device, and it's 8 qubit. So the first 3 devices here, IonQ, Rigetti, and Oxford Quantum Circuit, they are based on what is called gate-based system, where you have quantum circuits, like similar to classical circuits that are based on application of gates and so on and so forth. Albeit in this case, you have quantum gates, not the classical gates. Quera is what is called analog neutral atom QPU. So this is what is called analog Hamiltonian simulation device. So for Quera device, one doesn't have like quantum circuits. What one does is like in terms of Hamiltonians. So Hamiltonians are like mathematical objects to represent energy of a quantum energy of a system. So, and Hamiltonian is what drives the evolution of a quantum system. So if you can map the Hamiltonian in terms of the Hamiltonian of neutral atom systems, then one can encode the simulation problem on the Quera or neutral atom devices in a more hardware efficient way. So, that was about the quantum hardware. But as you know, quantum hardware is a scarce resource. Like all these devices are just like, for example, there are only 5 devices currently available through Amazon Bracket. So before you use this hardware, what you would like to do is you want to, first, build and test your algorithm, your code and everything. And for that, we have local and on-demand simulators. So local simulator is what is part of Bracket SDK. So if you install Bracket SDK on your local laptop, you can use this local simulator to just test rapidly, prototype your algorithms in a fast and convenient way. And the idea here is that to use local simulator, you do not need to use AWS cloud that uses your local computer's CPU and RAM. And using local simulator on a typical laptop, you can go up to 15 to 20 qubit devices you can easily simulate. If you want to go beyond 15 to 20 qubits, you would need to resort to the managed simulators. Like there is state vector simulator, density matrix, and tensor network simulators. I will be talking about these simulators as well, and when I show you AWS console. But quickly, state vector simulator is it goes up to 34 qubit. It stores the full wave function of your quantum system. So it requires a lot of memory. So like, for example, to go from 34 qubits to 35 qubits, you will need twice as much memory, right? And if you want to build a state vector simulator of 50 qubit, for instance, in today's technology, it's not possible because none of the supercomputers have that much memory to store the full wave function of 50 qubits. I think the largest state vector simulation that has been done is like either 46 or 47 qubits. Then there is density matrix simulator. So density matrix simulator is special in the sense that it can simulate noise as well. So I mean, the state vector simulator simulates an ideal quantum device, but if you want to simulate how noise affects your quantum results of your quantum circuit, density matrix simulator is way to go, and it goes up to 17 qubits. Then tensor network simulator is another simulator that does not store the entire wave function. It stores it encodes the quantum circuit into a structured graph, and that can go up to 50 qubits on Amazon Bracket. Okay, so before going ahead, are there any questions about these simulators? Okay, so I think the event engine that event should have started now. So let's try. Are IBM quantum computers available too? At the moment, no. Okay, so now I think you can go to that link. I'm pasting it here. You go to that access link. Everybody on Zoom, are you able to click on the link and see the landing page which asks you to sign in?
Yes, and I was able to sign in all the way through.
Okay, perfect. So if you click email one-time password, it will ask you to enter your email. I will enter my email up here, send passcode. You will need to wait a minute to get the passcode. Okay, mine is here. Okay, sure. Yeah, I'm sending the link to Zoom again. If you have any trouble, please click on that link. And here you will need to, you'll see that review and join, name is U Washington, September 20. And at the end, if you go at the bottom, you'll need to agree to the terms and conditions and then join event. Okay.
And that says event not started.
Oh, that says, okay. Everyone able to see this page and see that event ends in 3 days. So you will have access to this event for the next 3 days. So feel free to experiment even after this talk and familiarize yourself with the AWS Amazon Bracket. So I'll be going through this setup a little bit later, but let's do on the bottom left corner here, it says AWS account access. So click on Open AWS console, US East 1. If you do that, it will open a new tab. So this is what AWS console is. And we are interested in learning about bracket. So in the search bar, type Amazon bracket, click on Amazon bracket, and you will see this page appear. Okay. All right. So now I would like you to go to permissions and settings. Is everyone on Zoom able to follow and see the Amazon bracket dashboard? Okay.
Yeah, I can.
Perfect. Now we click on permissions and settings. And if you're here and if you see this button right here, you can say you can click on accept terms and enable. But if you already see this being enabled and this button is inactive, you're already okay. Don't need to do anything. Now you go to execution role, right? So service link role, it says the service link role already found. So if it says that link role already found, you don't need to do anything here. But if it does not, then you would need to create a service link role. Okay, but in this case, it already is good. Now it says hybrid job execution role. So you would need to verify existing role. Okay, no roles found. Okay, so that means I need to just create the default role by clicking the button up here. Okay, and if you see this error saying that failed to create role, that means no need to worry about. The way it works is that when we provision accounts for many participants, like 5 participants share with just 1 account. So in your team, if somebody has already created execution role, you don't need to create one. That you're already good. Was there a question on Zoom up here?
Yeah, I have a question. Hello.
Yes. Please go ahead.
On my console home, I couldn't find the Amazon bracket.
Okay, so if you on the console, if you don't see it, in the search bar, you can just type bracket.
Okay.
And this will pop up here, and you can just click on Amazon bracket.
Got it. Thank you.
Okay, so let me go through this again. So if you already are on Amazon bracket console up here with these menu dashboard devices and so on, what you need to do is click on permissions and settings. In general, enable third-party devices. You would need to make sure that this button is inactive. If it's inactive and says enabled, you're good to go. Go to execution role, service link role. If it says the link role already found, you're good to go. No need to do anything. Otherwise, just create a default role. Now, hybrid job execution role. Now you need to click verify existing roles, and it says the roles were found with sufficient permission. So you're okay with that. So we need to do these permissions and settings for a reason that first, like as I mentioned, the quantum hardware is a third-party device. So we need to set the proper permissions so that there is a proper communication between AWS cloud and the device for your account that has been provisioned, and then similarly link roles for hybrid job execution as well. Okay, now let's go to notebooks. Click on notebooks on the left menu up here, and what we would like to do is create notebook instance. Okay, is everyone with me on Zoom?
Yes, thank you.
All right, so in create notebook instance, just give some name, like I'm going to give my name to differentiate from other notebooks up here, and then you can leave everything else by default. So like except for visual mode, if you want dark mode, you can go with that. So what it's going to do, it's going to create a notebook instance with some GPU and CPU memory that is required up here, and then leaving everything else default, click on create notebook instance. Okay, now it says starting your notebook. So this usually takes 3 to 5 minutes. So what it's going to do under the hood is that it's going to provision an EC2 instance, which is Elastic Compute instance, and there it will create a Jupyter notebook for you there, and it takes like 3 to 5 minutes to do all that in the cloud. And while it's doing that, let's go back to the presentation and talk more about Amazon Braket, and before coming back to the notebook and do some fun stuff, basically running quantum circuits. Okay, so going back to the presentation. Okay, so I was talking about Amazon Braket SDK. Are there more questions on Zoom? Okay, all right. So Amazon Braket SDK, it's an open source Python library, and basically to do testing and prototyping, you don't need AWS account. All you need to do is basically pip install Amazon Braket SDK on your local laptop. So using Amazon Braket SDK, you can test your circuits and run your circuits using 3 local simulators, which are available for free, like Braket SV. So Braket SV refers to state vector, that's right. Braket DM refers to density matrix, and Braket AHS refers to analog Hamiltonian simulation. However, as I mentioned, the local simulators use the computing resources of your local computer, either desktop or laptop. So the capacity of the number of qubits would be limited by your laptop. So for local simulators, usually for a typical laptop, it could be 15 to 20 qubits. In addition to that, using Amazon Braket SDK, if you already have AWS clouds account set up for you, you can directly submit quantum tasks and jobs directly from your laptop. You don't need to go to AWS cloud, log into Amazon Braket dashboard up there and start a notebook. But so there are 2 different options to submit a job, basically. And there is already a very good GitHub page with all the documentation and everything about Amazon Braket that you can look at. Now, Braket works quite well with many open source plugins. For instance, if you might have heard of PennyLane, which is one of the leading, or probably the leading, open source plugin for quantum machine learning and quantum simulation. So PennyLane, it's a cross-platform Python library for programming quantum computers. So the PennyLane is already it's kind of a first-class citizen on Amazon Braket. It works very much in tandem with Amazon Braket. One can just do import PennyLane as QML and proceed with your programming. So if you have worked with PennyLane and you want to use that code directly on Amazon Braket, you can do that. So using PennyLane, what you can do is you can train a quantum computer the same way one trains classical neural network in typical machine learning pipeline. Then we have open source. In talking about open source plugins, we have what is called Qiskit Braket Provider. So Qiskit is the open source software package by IBM. So if you already have been working with Qiskit to develop your codes and so on, but you want to use the simulators, okay, a little bit of interruption here, and that is because we had clicked on the notebook that when the notebook starts, it notifies you. So that means the notebook has started. So we'll come back to this in a minute. Okay. Are we to click on Python SDK? No, we don't need to click on Python SDK. It's fine. David, did you mean to ask something else? I'm not sure what you mean to ask.
Okay, hello. So I have on the page where you have algorithm library, Python SDK, and developer guide. Are we to click any of those, or to just click open notebook instance is ready on that
Yeah, I'll
option there?
just give me a minute. I will show all that to you. Okay, I will guide you through
All
that
right.
dashboard. Okay, so we're talking about Qiskit bracket provider. So if you have a code that already written in Qiskit, you can just run that code verbatim on Amazon bracket and use the simulators and all other devices that you have available through Amazon bracket essentially. So Qiskit as it stand already on IBM, it's of course using Qiskit we can access to IBM quantum computers, but the idea here is that with this kind of plugin, Qiskit bracket provider, you can also use your Qiskit code to run on different kind of hardwares available in Amazon bracket. Okay, now we go to the fun part, that is hands-on lab. So I will stop the presentation now and switch to. Okay, so this is the dashboard of Amazon bracket essentially. So if you go to click on dashboard here, you will see several kind of announcements. So these announcements are like whenever there is a scheduled maintenance or update in the availability of various devices and so on, those are updated here regularly. As you can see, there is some announcement related to availability of IonQ and so on. Then there's community support using Linkroot Stack Exchange if you have any questions, or you can already see what kind of other discussions have been going on regarding Amazon bracket. Then there is AWS Quantum Computing blog. So in this blog, there are articles written by many customers or even the research scientists at Amazon, educating about what has been done and what can be done using Amazon bracket in terms of quantum computing. Then there are resources. So in resources, if you click on Amazon bracket Python SDK, it will take you to the GitHub page or to the documentation page. So you can learn all about different components and everything about Amazon bracket up here. Then there's a developer guide. You can, if you want to dive deeper, there's a very good documentation there. And algorithm library is essentially it's a for example, if you click on algorithm library here, it shows like there are notebooks, Jupyter notebooks already created for you, teaching about the standard algorithms, textbook algorithms that you can run on quantum simulators and also try on quantum hardware if you will, to educate yourself and test and develop understanding of these algorithms. So going back to the dashboard, now we click on devices. So in devices, if you see, there's a list that pops up here. So the first is SP1, state vector 1. So if you click on state vector 1, it says status online and next available now. So all the simulators like state vector 1, density matrix 1, and density network 1, they're available all the time, 24 hours. And if you see this device ARN, so this is what is called the Amazon resource name. So this is like the identifier for this resource, this device. And whenever we want to run a task, a quantum task on state vector 1, we will specify this identifier in our code, and the code will run on this device. The same code can be run on different device just by changing the device ARN to something else. For instance, if you have a code that runs on state vector 1, but you want to run on tensor network 1, you can just change one line and give the identifier for the tensor network simulator, and you will get there. And similarly, if you want to run the same code on a quantum hardware, for instance on Harmony, you will need to just copy the identifier or ARN for how many devices, right? So so ARIA1, so there is ARIA1 and ARIA2. So ARIA1 and ARIA2 are the same device, devices basically. It's just that they are duplicate. So if one is offline, the other one becomes available. So ARIA2 is available right now. And if you click in here, there's a lot of detail about what this device is all about, right? Who is the hardware provider? An important thing is the cost. So the cost of this device is given here. So the cost of quantum devices is broken into two parts. Like first is task, and then there's short, right? So a task is like every time you make a submit a quantum circuit to the quantum device, that's a task. You are asking it to do something for you. Now, if you go into further level of deeper, any quantum circuit that you run, you might be aware that you want to build statistics on your results. So, for example, if you want to run the quantum circuit just one time, that is one shot. And usually, like you run it multiple times, 1,000 or 2,000 times, to build statistics on your result to get to understand what's the highest probability result that quantum circuit is giving to you. So that is short. So for instance, if you want to run one quantum task with 1,000 shots on ARIA2, it will cost you $30.30. So that's a little bit expensive because this device is expensive. If you look on calibration, so the calibration gives you the topology of the device. So these are all different qubits, and these all qubits are connected with each other directly. So that has an advantage that if you want to run a two qubit gate, all qubits are directly connected with each other. So there is latency is quite low. So that is one of the reasons why this device is kind of more expensive. And then there's a calibration data available about fidelity of one qubit and two qubit gates up here, and so on. So these are available up here. Now, if we compare that with the Rigetti device, that is Aspen M3, the cost you see is for Rigetti device is significantly low in number of shots. It's for the same quantum task that was that would have taken $30 to run on IonQ can be run on for 65 cents here, because Rigetti is much cheaper. And if you look at calibration, so calibration of all the 79 qubits up here is like this. So as you can see, not all qubits are connected directly with each other, right? There's a path between. For instance, if you want to run a 2-qubit circuit between qubit 10 and 27, then what one will have to go through is what is called swap gates. So swap gates will find a path between this and like this to go through 11, 12, 25, 26, and then 27. So that definitely adds some latency to the performance. So that's that.
What are some of the links missing in this diagram?
Yeah, so that is what I was telling, that this is the topology of the qubits. Not all qubits are directly connected with each other.
Right, it's not a complete graph, but there's sort of a regular pattern here. That's selected edges seem to be missing. For example, 11 to 26 is missing,
Right.
but 1 to 16 is present. So is that just by design part of the process?
Yeah, I think that is something, a design consideration. There may be something like a reason why this is not connected. I'm not too sure why they are not connected, but that is what the diagram is. Do you need to understand the topology to program something? No, you do not need to understand the topology to program something. So when you write a program in Amazon Bracket, that is hardware agnostic. That doesn't, that doesn't require you to know how different qubits are connected with each other. What happens is that when you write a code, and so before that code actually runs on quantum computer, there's transpiling going on. So, like for example, if you want to run provision, like there's a gate called C0 gate. So if you run a C0 gate, so C0 gate is not a native gate on all different hardwares, right? So all hardwares have their own native gates. So C0 gate is broken in terms of in terms of those native gates, and then there is a very low level code that is in the language of that particular quantum hardware that runs on the hardware. But this process is you're completely blind to that, and you don't need to know that to run your program and get results. That's a very good question. Okay, going back to the devices, I mean, although we will not be dealing with Aquila today, but Aquila is a neutral atom device, and that can go up to 256 qubits. And if you are interested in learning about that, maybe we can schedule another session in a week or 2 weeks or so. That will have to be totally on Zoom because I will not be in Seattle for that. So yeah, so that's about devices basically. Another thing I would like to mention is that the simulators. So the cost of the simulator is not through task and shot; it is per minute, right? So any guesses why? Why do you think there is the cost estimate for the simulator is different from the cost estimation of the device? Can you take a guess why that is? Anyone?
The simulator is running on the standard machines, so that it's cheaper.
Yeah, exactly. So more than cheaper, I mean, the idea is that the simulators, they use classical computing resources, just like our CPUs and GPUs, right? And the CPUs and GPUs, they are just timed in terms of how much time it takes the job to run. There is no other considerations. Whereas when you run on a quantum computer, when you submit a task to a quantum computer, and depending on how many shots you use, the quantum computer might be busy for a longer or a shorter period of time. So the charge is done, the cost depends on the number of shots and tasks. Okay, so now let's go to notebooks. So as you can see, as I was mentioning, that each account that is provisioned is shared by multiple people. So the account in which I am in, there is shared by Ramin, Jacob, and me, right? And then other participants will have that similarly shared accounts within the team. So let's click on this link URL up here, but in my case, it's already been clicked. So okay, so if you click the URL here, okay, let's do that. It will open a Jupyter Lab for you. So Jupyter Lab is opened. Okay, so is everybody with me until this point on Zoom?
Yes.
Yes, I am.
Perfect.
Yeah.
Very good. Okay, so now, so there are two folders here, bracket algorithm. If you click on bracket algorithms, double click, there's a textbook and advanced algorithms. So if you double click on textbook, there are many textbook algorithms, the famous algorithms that there are corresponding notebooks. For example, Bernstein Vazirani, there's a notebook, you can run this notebook by yourself and see, teach yourself what this is all about. But now let's go to bracket examples. And in bracket examples, click on this getting started, right? And getting started, there's another folder, getting started. And then there's the notebook is also called getting started. So let's click on getting started up here. Okay. So now what we're going to do is basically run a very simple quantum circuit using local simulator and convince ourselves that Amazon Bracket does indeed do what I have been talking about so far. So just some general imports. You will need to import this circuit module from bracket.circuits, and then local simulator as a part of the package. Let me just zoom in a little bit for better view. Okay. All right, so you can run the first cell. You can do this on the go as I'm working through this. Okay, then build a circuit. So what we're going to do is build a very simple circuit. It's called Bell circuit. So we start with a circuit, this object. So when you start with a circuit object, it's an empty circuit, right? And when you add a Hadamard gate, so are you familiar with basic quantum gates at all? Not really. Okay. All right. Okay, then let me try to find out a different presentation and give a quick introduction of various kind of gates. I was not aware of that part, but I would have prepared for that. Okay, so very quickly, I will run down what qubits and gates look like. So in quantum computing, the basic unit of computing is called qubit. Just as the classical bits, there is qubit, right? So a qubit can be either in position 0 or 1, or in a superposition of 0 and 1, right? So a qubit, state of a qubit can be written such as this: psi, ket psi is alpha times 0 plus beta times ket 1. So alpha and beta just represent the amplitude with which amplitude of the superposition between state 0 and 1. If you look at this diagram, the state of a qubit can be represented by this sphere. Like on the north pole, there is 0. On the south pole, there is 1. And between all this, on this sphere, these states can be spanned by this parameter theta and phi. So all these states are accessible to a qubit, but this was not possible in a classical qubit, right? So theta and phi are two parameters that decide the amplitude alpha and beta of the state of the qubit. And ultimately, for a measurement, the idea is that it's normalized. That is, mod alpha square plus mod beta square has to be 1. Okay. Then what does a quantum gate mean? So a quantum gate means a single qubit quantum gate means that it does some kind of rotation, some transformation. Like let's say initial qubit was in some position like this. So a quantum gate, what it does, it just performs a rotation on this Bloch sphere. Right? It can take this particular vector pointing in this direction to point in this direction, and so on and so forth. So that's what quantum gate does. Going to the next slide. Not all classical gates are directly available on quantum gates, because quantum computing is quite different, or the other way, like not all quantum gates can be simulated by classical gates, right? So first, a similar gate, for instance, this, let me just show right here. So this is called Pauli X gate. Let me move this down here. So this is Pauli X gate. This is very similar to the NOT gate that is available in classical computing, right? So like, if you start with state A, the final state is A bar, right? So in this truth table, if you go, if the initial state of qubit is 0, it goes to 1, or if it's 1, it goes to 0. So that is what a Pauli NOT gate is. Okay. Then there is control NOT gate. So there is a classical analog of this X gate, Pauli X gate, in the classical computing, right? And classical, that is simply the NOT gate. However, the controlled NOT gate is a special gate in quantum computing, which generates entanglement between two qubits, right? So the way it works is that we have two qubits, A and B. Then the state of the B second qubit changes depending on the state of the first one, right? And the way it works is that if the state of the first qubit is 0, then there is no change in the state of the second qubit. But if the state of the first qubit A is 1, then there is a bit flip, right? For instance, what you can do is look at this truth table. So if state is A is 0, B is 0, so there is no change in B, and A always remains unchanged. Okay, can you guess what will be the answer for this one if I go to in the second line? 0, 1. That's right. There's a question here: is gate just operator in normal? So a gate is it is an operation. It's a unitary operation, just like in normal quantum mechanics. That's right. Okay. Now, can we guess the output in the third line? Zoom participants can feel free to either say it on the mic or just write in the chat. 1 0 1 1. So it's going to be 1 1. The reason is that the way it works, as I explained, that if the state of the first qubit is 1, then there's a bit flip in the second. So the state will be 1 1. Now, what will be output of the last one? 1 0, indeed. So this goes to 1 0. Okay. Now this gate is called controlled NOT gate because there's a bit flip going on in state B, but there's a control on the first qubit A. So state of qubit A or the first qubit controls the NOT operation on the second one. That's why it's a control NOT gate. And the specialty of control NOT gate is that it cannot be simulated by any classical gate. Like, there is no equivalent classical gate that can simulate this kind of truth table or behavior. Now there's a special gate called Hadamard gate. So Hadamard gate, what it does is that it generates superposition, equal superposition. Like if you start with the state 0, the application of Hadamard state takes it to the state 0 plus 1 over square root 2, right? But if you start with 1, it takes it 0 minus 1 over square root 2, right? So these both are equal superposition state. However, there's a plus and minus sign difference. Okay, so that's what Hadamard state does. Hadamard gate does. So there are two important phenomena in quantum mechanics, and that is, first is superposition, and the second is entanglement, right? So superposition and entanglement hold the key to all the amazing things that quantum computing can do. And Hadamard gate does superposition for you, and control NOT gate does entanglement for you, right? So these two gates are quite important in quantum mechanics, in quantum computing. All right. So now let's build a very foundational quantum circuit with the two gates that we just learned, like Hadamard superposition and C0 entanglement. So we take two qubits, right? There's a Hadamard gate and there's a control NOT gate, right? So if you do some computation here, after applying Hadamard on 0, it will get a 0 plus 1 over square root 2, and then these are two possibilities of the output state you will get at the end. This has a special name, and this is called a Bell circuit or Bell state. And this is what is called the maximally entangled, 2-qubit state up here. And the state of the final state of the circuit can be written as 0 0 plus 1 1 over square root 2. Okay. Now what one can do is one can go beyond just 2-qubit and apply an array of these C0 gates, and this is called GHZ circuit. This is in a way generalization of Bell circuit to multiple qubits. So we'll be working with these two types of device, circuits. Very simple to understand, yet very non-trivial in their function in our demo today. Okay, now that we are expert in quantum computing, we can go back to go back here. All right. So Bell circuit is circuit, and there's a Hadamard gate we just applied, and there is a CNOT gate controlled on 0 and target 1. Now you can convince yourself whether this is the same circuit or not. If you do print, it's taking some time to run. So what are Bell inequalities? So Bell inequalities basically it's a statement in quantum mechanics showing that any state that you generate, the entanglement between those states will be less than the maximally entangled state up here, showed by that we just showed 0, 0 plus 1, 1 divided by square root 2. So it has been determined that for a 2-qubit state, this 2-qubit system, the maximally entangled state is this one, this Bell circuit. I don't know what is wrong with this. Let me just restart the kernel. You ran. Okay, that's fine. That's good. Restart, select. Okay, Bell. Now print Bell. So this is the Bell circuit up here, right? Hadamard and control mod. Okay. Now we'll use just the local simulator to run this circuit. This circuit got Bell with 1,000 shots, right? So 1,000 shots means we'll run this circuit 1,000 number of times, and we'll see what the output is going to be like, each output. Okay. So I ran this, and it turns out that out of those 1,000, 503 times the output was 0, 0, and 497 times the output was 1, 1. And if you remember, the output of a Bell circuit was 0, 0 plus 1, 1 divided by square root 2, right? So that means the outcome has to be equally divided between 0, 0 and 1, 1. Okay, so this is almost equal, 503 and 497. And since quantum computing is probabilistic, the results are always going to be not exactly half and half, but with some difference, right? And as you increase the number of shots, that difference will shorten further and further, right? Now we can just plot how it looks like in bar graph, and voila. So this is what the result of Bell circuit is, that we have just simulated using a local simulator. Now let's go one step beyond and run these circuits on simulators, right? So for simulators, if you go to getting started, the folder that starts with 1, running quantum circuits on simulator, click on that. So now we have this notebook up here that we can run, and just do some basic imports to import like matplotlib, circuit observables, and especially this object called AWS device. And now we'll be using, what we'll do is work with the GHZ circuit, that is generalization of Bell circuit up here. So we can just write a little program here to, write this circuit, right? So first instantiate the circuit object. This is a blank circuit. There is nothing in. Oh, GHZ is a Greenberger GHZ state. Yeah, Greenberger, Horn, and Zeilinger state. So that is there's a very important state in quantum computing, because this was the first time GHZ state was the first time that was realized in the lab beyond 2-qubit gate, and showing that this is indeed a maximally entangled state for 3 qubits.
It's an extension of the Bell IP.
Yeah, but for more than 2 qubits, and it's quite not trivial to realize that in experiment. Okay, so yeah, so we start with the circuit object, and then add a Hadamard gate on the first one, and the series of CNOT gates. Now let's just do with at 10 qubits and print GHZ circuit. This is what it looks like. And in local simulator, just as we did with the Bell, you can say that device is local simulator, and device.run GHZ with 1,000 number of shots. And we expect result like this, like all zeros and all ones equally divided in 22. And this is what the bar graph looks like. So far what we did up here is the same thing what we did with the Bell circuit, but with with GHZ circuit here with local simulator. Now, if you're interested in computing expectation value of some observables, like observable of Z observable, you can also do that up here. And I will leave that as an exercise for later because I want to get to more interesting things up here. So you can do that, and then yeah, there's an important thing here. Like when you put shots equal to 0, that means the circuit doesn't run on a quantum computer. What it does basically in that case, for shots equal to 0, it analytically computes what the output state is going to be, and then just outputs it for you. So, but in this case, this is what it does. This the state vector, it looks like only the first and the last entry have non-zero output. Rest all are 0. Okay. Now let's run on these the on-demand simulator, the state vector and tensor network simulator. So for that, to run on state vector, what you would need to do is call device equal to AWS device, and remember that ARN, the Amazon resource number, and that is up here. If you run this, now device is set to the state vector simulator. Let's say we want to run 15-qubit GHZ circuit with 1,000 shots, and you can do all this and you can run this. And what it does basically, it runs it. It is taking some time. Oh, it's already finished. And then it prints out what the count is going to be. So count is like 510 times, all zeros 510 times, all ones 490 times. And this is what the result is like. Similarly, you can do that with tensor network simulator. No surprises there. You will have similar results. And at the end, like what you can do is estimate what the cost of this whole thing is going to be, and it turns out this is just 3 cents. It would take 3 cents to run this circuit on tensor network simulator. Okay, so that's all about simulator I want to talk about up here. I want to now go to QPUs and try to run this on an available QPU, right? So
the fundamental gates that you have available with a C0 and the Hanamar,
yeah.
Are there any other gates in the toolbox, or are these just those 2?
Oh no, so there are many gates available. Like there's like X gate. There are rotation gates, like rotation around X-axis in.
So if I'm using the phase angle.
Yes, exactly. RX gate, RY gate, RZ gate, and all that. So there are a plethora of gates, quantum gates available. And it's good that you asked, because that's the next thing I'm going to talk about right now. Okay. So like running quantum circuits on QPU device. So here I would ask you not to run on QPU right now, because if we all try to submit the job to the quantum computer at the same time, we all are going to be queued in there. So I will run the job, try to submit the task from here and see if it completes or it's queued. It is queued or not. Okay. So running quantum on QPU device, some just general imports, right? Now here, the answer to Rob's question. There are multiple gates, different kind of gates available. Like there is a CC0 gate, like double control NOT gate, C0 gate, phase shift gate, control phase shift. Then there is like a swap gate, X gate, Y gate, and all kind of rotation RX, Y all are available in Amazon Bracket. Then there are gates supported by Rigetti device. So these are the gates supported by Rigetti device, like a control Z gate, XY gate, double control NOT gate, RXY, RC, and so on. But you can ask, like, what if there's a gate that is not available in the gate supported by Rigetti? So in that case, that particular gate will have to be, compiled in terms of these gates. And then gates supported by IonQ device are these, and so on and so forth. So now let's just do the same exercise up here. We define a bell circuit, and local simulator is something we have already run. So now let's quickly jump to the hardware Rigetti. So if you go back to bracket console and go to devices, unfortunately Rigetti is not available right now, but Harmony and ARIA2 are available. But ARIA2 usually is quite busy. So let's run it on Harmony device. So to Harmony, and I copy this ARN up here, and IonQ. Oh, the Harmony is already copied up here in this section, and I write IonQ as AWS device, and so on. And let's try to submit this task. So that it says the quantum task is created. If you go back up here, look at quantum task. So this is a task that I have created. It is right now in the queue to run. It can take some time to run. In the meantime, quantum task, what we would like to do is we would like to see how the results look like. So I am just going to copy this plotting. Okay, so if you go back here, oh, somebody else also submitted a task. That's okay, but I would ask you not to do any more further, because that can create a long queue. Okay, so what we can do is we can go ahead with this presentation, and we can come back to it, and hopefully by then the queuing will have this job would have already completed. Let's see. It is still queued. That's fine, no problem. We can come back to it later, I think. But let me show you something here. I already have the results saved from a different run from before on Rigetti device. And as you can see, unlike what we were seeing in when we ran on local simulator or state vector simulator, we have counts from 1, 0 and 0, 1 as well, right? For simulators, the bar graph only showed entries from 0, 0 and 1, 1. Why do you think that is? Any guesses? Like, is this normal?
Is it due to noise?
Exactly. So this is due to noise, because the devices are not, quantum devices are not perfect. So due to noise, there is always going to be some error up here. And that is what this is showing up, right? But still, as you can see, the higher probability is that for 0, 0 and 1, 1. So actually, this is what I wanted to actually show you by running actually on the quantum hardware. But let's see what the status of, oh, canceled. Okay, this one is queued. Did somebody cancel their job on Harmony? That's okay, no problem. Yeah, so are there any questions regarding this at this point? Whatever we have discussed so far, like we discussed what Amazon bracket looks like, quantum gates, what how we can build quantum circuit with quantum gates, we ran these quantum circuits, very basic quantum circuits on local simulators, state vector simulator, and also we have submitted a task to IonQ device. So I think this is a good point to take a break, and I'll open the floor for any questions that you might have. Okay, if there are no more questions, we can take 10 to 15 minutes break, maybe. In the meantime, are there any questions on Zoom? Feel free to write them in the chat or speak up. Yes.
Regarding if you run multiple shots, can you get shot for shot readout of the data?
Oh yeah, that's a very good question. Let me show you. Okay, so this is a job, or today when we ran on state vector simulator up here. Okay, so if you click on this URL, right, and there is results. See results in S3. So S3 is like simple storage bucket, and there's this file called results.json. All you need to do is download this file. It's up here, and open this. It opens on Mozilla for some reason. That's fine. So, but you can open this file anywhere you like. And this file has this bracket schema header. So it's telling just like the name and the version of the software, and then measurements. So this is the outcome of all the 1,000 shots that we did, right? If you scroll, like all different, it goes up to all the way up to 1,000, basically. Okay, you can trust me on that. Now, if you click on measurements, the first measurement, there are 15 qubits that we ran. So first measurement was all zeros. The second measurement was also all zero, and some random like 17th measurement was also on all zero, 26 also all zero. Okay. I just want to show all one. Yeah. So 46 measurement was all one. So this is the way you can look at all the measurements up here. Okay.
So we have coffee and refreshments available out in the main area. We can lead everyone there.
Yeah, I'll just point you to, so go past the elevators here and just angle off to the right. The far corner over there, that's coffee.
Okay.
So help yourself. And that one is down here.
Sure.
We'll come back and
somebody said like we cannot hear the question. So the question basically was, can we see the outcome of all different shots that we submit to the quantum circuit? Like for example, we submitted 1,000 shots. What are the outcomes of each individual shots? And that's what I showed you, that you can go to Quantum Task, download this JSON file, which has all the results stored in it. Does that answer your question, Ramin? Perfect. Yeah. So we can be back in 10 minutes, do you think? Okay, so shall we get started?
Yeah.
Okay, so welcome back, everyone. Now we'll be
check to make sure everybody can hear you.
yes. On Zoom, can everyone hear me?
Yep.
Okay, perfect. Okay, now let's go on to the next part of the talk, that is called hybrid jobs. So far, what we did was, write a quantum circuit, and we just directly submitted it to a quantum hardware. Oh, let's check on the status on the quantum hardware. Quantum tasks. Oh, it's completed. So if I go back up here and try to see the results, as we see that results have also some contribution from 1, 0 and 0, 1 as well. And if I plot that you'll say 0011 and 1001. So this is a result from actual QPU that we just ran, like the IonQ Harmony device. Good. So now, okay, let's go back to it. So what we did was submit a quantum circuit directly to a quantum computer. We got results and we were very happy. But but as I mentioned, like in practice today, what one does is that run a hybrid algorithm where part of the program runs on classical computers and part of the other part is run on quantum computers. So let's talk about that and let's see how we can provision that on Amazon Braket. So hybrid classical and quantum algorithms are in a way, working with classical computer and quantum computer at the same time in tandem, so that quantum computer acts as a co-processor. It's similar to what we do in terms when we use GPUs, right? So we have like let's say you're training a neural network or whatever. There is a part of computation like that requires like very fast computing, and GPUs are quite good at that. So what we do is we resort that part of computing to GPUs, and then GPUs compute the error function or objective function, give it back to the CPUs, and CPU does the optimization part. So that is what happens in a hybrid classical and quantum algorithm. Like one pre-processes and post-processes everything on classical computer, and the quantum circuit is then fed to quantum computer to run and get the result, right? So hybrid algorithms with Amazon Braket, like what you can do is in Amazon Braket, you can write your own hybrid algorithms. There's a growing list of examples that you can see on Amazon Braket SDK's documentation and webpage as well. Then there is PennyLane. PennyLane is I think the torchbearer in terms of quantum machine learning and hybrid algorithms. So you can use PennyLane directly on Amazon Braket to run hybrid jobs. And then there is hybrid jobs, Braket hybrid jobs. So Braket hybrid jobs is a feature that lets you build all these programs using either PennyLane or your own algorithms and submit to AWS cloud or Amazon Braket to run that in an efficient manner. And what do I mean by that? I'll explain now. Okay. So when you in this presentation so far, we talked about shots. So shots are basically, if you run a quantum circuit just once, that is one shot. Okay. What you can do is we can combine number of shots in a quantum task, right? A series of repeated shots on a device that is called a quantum task. Now, a further level up, if you go in hybrid jobs, so hybrid job is like sequence of classical and quantum computer cycles where you are trying to submit many quantum tasks as part of the whole computation, right? For example, let's say you are working on a machine learning algorithm, quantum machine learning algorithm, and there is a gradient descent method, let's say. And at each iteration, what you need to do is you need to compute the value of the objective function and the gradient, for example. So in that case, in first iteration, there is some processing done on classical computer. It goes to quantum computer, and a task is submitted. The result one gets, and then you feed back to the classical computer. Like this cycle shows exactly that. So what hybrid job does is like it gives priority access to quantum hardware that until this whole job is completed, I mean, there is no interruption in between. So hybrid job basically facilitates that. So at a glance, basically, as a user, you have access to job instance. So job instance is basically a shared shared responsibility between or like a shared part of tasks on demand simulators, QPUs, and the classical computer as well, just as I described. So and the idea is that using this the proper division of tasks on classical and computing and quantum computing resources, one can optimize performance on the next devices, and that's what hybrid job does for you. And then there's a priority access to QPU, right? If you are running a hybrid job, when the until the job is completed, either in terms of cost or like some kind of convergence in the error function, or like in convergence in your whatever metric you have defined, the QPUs are available to hybrid jobs on a priority basis. So hybrid job basically is similar to what we described before, that is part of AWS cloud, and there's this job instance. So job instance basically is a combination of the classical part of the program and the quantum part of the program, and that is run on Amazon Braket, right? So a job instance, for example, the classical EC2 instance to manage hybrid job execution, like to manage this running of the program on the classical and on a quantum computer, there is a EC2 instance that is deployed. Then there are 3 pre-built containers. So you can use either you can use these pre-built containers. So these containers basically have some pre-built programs such as PennyLane, TensorFlow, PyTorch, and other useful libraries. But again, if those are not enough, and if you want to bring your own software package or something that is not available here, you can bring that through custom containers as well. So you can containerize your all your packages and store into what is called Amazon Elastic Container Registry, and then Amazon Braket job instance will be able to access that. So that is facilitated through all these hybrid jobs. Now, there's a feature called Amazon Cloud Watch, which lets you monitor the progress of your of this whole, like for example, machine learning pipeline through different metrics that you define, and we'll be seeing that shortly. Then again, mention that priority access to quantum hardware until the job completes. The hardware is locked in until the job is completed, basically. Now, so we discussed about local simulator and the managed simulators as well, but there's through this feature called embedded simulator. If you want to bring another simulator from outside, for example, PennyLane has this lightning fast lightning simulator, basically. So that is a simulator, lightning qubit simulator. So lightning qubit and lightning GPU simulator, which can also be used through hybrid jobs if you want to use that, right? So, and that can also be done through containers. Like, so in that container, you can load the favorite simulator that you have, or any embedded simulator from PennyLane, and that can be used in the program as well. Okay, so let's do a hands-on lab to understand how hybrid jobs work. Okay, so let's go back here and getting started. Bracket examples. Should look at hybrid jobs. Creating your first hybrid job. Yeah. So let me go back. Bracket examples, hybrid jobs, creating your first hybrid job, and then this notebook called creating your first hybrid job, IPyNP, right? So this basically tells you how you can work with Amazon Braket hybrid jobs. So I encourage you to take some time and read through this notebook and familiarize yourself. But let me just go ahead and talk about what this code is. So in this, as you can see, like there is this notebook, and then there is algorithm script. Okay, so the way it works is that when you create a first hybrid, your hybrid job, basically you can, what you can do is you can import this AWS Quantum job thing, like the module. And what it does is like you call AWS Quantum job and create. So create a job. What you to tell it to be like a device, on what device you want to run, and the script, the algorithm script that you want to run. Okay, and since this is a simple circuit, there's not many parameters up here. So when you run this, it goes in the background and tries to create a job for you. Okay, so it is initializing on bracket. In the meantime, let's see what this algorithm script looks like. So in this hybrid job, what we are trying to do is first there's some basic imports, and the idea is that here, like in this script, this AWS, just as what we did with the simulators, device equal to AWS device, instead of giving ARN up here, we are using this environment variable Amazon bracket device ARN, and this is basically passed on from this object called device up here in the bracket jobs, in the hybrid job submission. Now let's look at what this is trying to do. It's trying to simulate a circuit here, and circuit has just one RX gate, rotation around x-axis with some angle, right? So what it's trying to do is trying to find out how this the outcome of RX gate is going to be if you rotate it out on different angles, right? So it's a very simple circuit, and then you create this task. So in this loop, you see from range from I to range 5, in each iteration there is a task being created, like device.run, this random circuit that is with RX gate, rotation around x-axis on qubit 0 with some angle, right? And the angle is, in each iteration, angle is changing, right? So what we are doing is device.run random circuit with 100 shots, and then we are compiling results. So hybrid job here, this is the quantum part up here. This is the quantum part, and it's being done iteratively over and over again. And these are all classical tasks, like classical post-processing. What is the count? What is the angle list, count list, and so on and so forth. So in this way, it's hybrid, that it's combining both the processing on the classical computers and the quantum computer at the same time. Okay, now we can go back and see. So it takes like about 5 minutes to complete. But let's go back, go to this Amazon bracket console, and if you click on hybrid jobs, you see that there is a job that I created just now. It's running right now. Okay, and it's using state vector 1 simulator as we had. If we click on here, it says it's running. It has the runtime so far is 2 minutes 40 seconds. There are some details about the similar to the devices. There is an ARN for hybrid job as well. For this job, there's an identifier that you can use later to find out the metadata about this job. Then there is.
Sorry, how
Sure.
are we navigating to this? I missed that.
Okay, sure. If you go back to the Amazon bracket console,
Yep, there.
on the left side, on the menu, there is hybrid jobs,
Thank you.
right? And then there is like all these details are available. If you go to view, click on view on CloudWatch. So this is where you can use it to monitor things. Yeah, so in CloudWatch, there is this job that is already there, bracket default job. If you click in there, it gives you all the information about how the job was done, like standard output and everything. like test job created, and then there's some metric like timestamps, total cost, iteration number, and it's running. So we ran for 5 iterations, and this is what it's showing, that it ran for 5 iterations, and it says test job completed and code run finished. In yeah. So in this job, we did not create any metric, but in the next example that I will show you what else you can do with CloudWatch. But going back here, this job is completed, and yeah. So in the algorithm script, what we had was, it's a very simple script where the entry point is basically the main program itself. But if instead of like starting with the default starting point, if you want to like have an entry point that is separate from the main function, you can specify that as well here. Like for example, starting function can be written to be something else, and then that can run properly. In the same way, the source module can be put in another folder here, algorithm folder, for example, and that can be used directly there as well. Now, checking hybrid job state, like you can click here to see what it says completed, and you can look at the results now. Okay, so results are basically job.result, and we just print out for different number of counts what are the angles were and what were the output, and that's what this is. Telling us. So counts basically, like in the first iteration, the measurement was 0 82 times, 1 18 times. So remember, this is a 1 qubit circuit, very simple one, and these were the angles basically. Okay, and if you want to download the results, it can be downloaded to local directory, and this is where the model.tar. You can unzip this file and see the results for yourself. I understand that this is a lot to take for hybrid jobs, but let me go ahead and show the power of hybrid jobs with another example that is called optimization of max-cut problem up here. So any questions so far on this? I didn't catch, how did you run the case? So when you, in the hybrid jobs, when we run this cell, job equals to AWS quantum dot create, it creates the job for you, where the algorithm script is provided, and it runs. Does that answer your question, Xinfeng?
Hi, thank you. I'm just curious, when you click, how do you execute it? There's no, you just highlight that and then click on the source module?
Oh, no, you just run this cell. This is a Python notebook.
Right. Usually you click on something like run. How do I actually run it?
Highlight the cell and hold down the shift and hit enter.
I mean, if you go to this cell,
Yeah.
you don't need to highlight. I mean, you just like shift enter.
Oh, shift and okay. Thank you.
Does that work for you?
Yeah, I'll give it a try. Thank you.
Perfect. Okay. All right. Now moving on. Let's talk about something more interesting. And I think in this example, the feature of hybrid job will become more apparent, more clear. So what I would like to do is talk to you about doing optimization with Amazon Bracket, right? And the problem that I'm going to work with is called QAOA. It's quantum approximate optimization algorithm. Okay. So the idea is that, like, I don't need to tell you that optimization problems are everywhere in all sorts of industry, manufacturing, logistics, finance, and whatnot. What we are going to do here today is take an example of the max cut problem. So max cut problem is an NP-hard problem. That is, if the size of the graph is too large, the requirement for classical algorithms grows exponentially. The problem essentially is that given a graph, right, what we want to do is we want to cut the graph in two pieces in such a way that there are maximum number of edges cut between. For instance, in this graph, this will be the cut. This will be the separation of vertices, so that this is a cut. So in one subset, you have this and this vertex, and in the other subset, you have these vertices. So how many edges there are between these two subsets? Like 1, 2, 3, 4, 5. So basically, like, all the edges are cut here. So this is called the max cut problem, and this becomes quite hard to solve if the graph becomes very large. Do we have any access to the hardware? I mean, can we design hardware by use of this method? I mean, you have access to hardware, as in you can submit the job to hardware, but I'm not sure. I mean, I understand. Can we design hardware by use of this method? What do you mean by that question, Raman? I mean, the hardware is already designed for you. You can design your algorithm. You can design a quantum circuit that you can then submit to quantum hardware to run. Oh, changing the hardware side of the problem. Yes, I mean, in this example up here, which we are showing, you can change the device. Like, instead of using the simulated SV1 here, you can put the identifier, Amazon resource name of a particular hardware that can go up here. For example, if you want to run this on Harmony, then you go to devices, click on Harmony, copy this ARN, go back here, and in devices, you can just put that ARN up here, and it will run on that device, Harmony device. The rest, everything remains just the same. Does that answer your question, Raman? Maybe changing the couplings between the qubits. So that is a non-trivial task, and that has to be done in the lab. So we don't have access to that. Those are already built in for you. I mean, it's like having access to an HPC from outside, right? All the networking and everything is already decided for you. You cannot change the networking. Those are like matters of hardware design. Okay. So in this problem, in the max cut problem, what we are trying to do is formulate as an optimization problem. So the idea is that we formulate an objective function such as this, like summation over all the edges, 1 minus Si and Sj, where Si basically takes two values, -1 and +1. So for this simple graph, we already see that this partition, so that these two edges are 1 and these three edges are -1, gives us the max cut, maximum cut answer. So so this objective function, if you see, like if Si and Sj, you run over all edges. So if let's say consider this edge -1 and 1, right? So Si is -1, Sj is 1. So that means Si times Sj will be -1, and 1 minus -1 becomes 2, and then divide by half. So if there is an edge between -n and 1, that will give a weight to the objective function. But let's say if you want to consider minus n and minus 1, same sign, minus 1 and minus 1, this will give 0 contribution to the objective function. Okay, and then at the end, you can take this objective function, run over all pair of in the vertices up here, and minimize that objective function to find out the maximum cut. Okay, so this is the classical formulation which we just visited. For quantum formulation, what one can do is map this Si and Sj variable to what is called Pauli spin operator, which has eigenvalues basically -1 and +1, right? So the idea is that we have this Hamiltonian, and at the end, what we are looking for is a solution which has the highest energy eigenstate S, so that this value, this whole parameter objective function is maximized. Okay, so that is what basically the quantum formulation is. And for this quantum formulation, we would need to design a quantum circuit and make measurements on that quantum circuit and find out like what partition of the graph gives us the maximum value of this Hamiltonian up here. Okay, so now it's going to go a lot more technical, quantum approximate optimization algorithm, which I think may not be like the best thing to do up here because that requires a little bit more. So I'll try to simplify that, and I'll just mention you that for any like quantum approximate optimization algorithm, what you do is you build a parameterized quantum circuit. Okay, so let's say there are 2 qubits up here, and there are some gates which comes with some parameters. And similar to machine learning, classical machine learning, like in neural networks, a neural network comes with like free weights. Those are parameters of the neural network. And in that machine learning pipeline, what you're trying to do, you're trying to find out the optimal value of those weights that gives you the minimum of objective function or a maximum of objective function. So that is what is done here as well. Like we have some quantum circuit with some free parameters, and these free parameters, every time there is an iteration, these free parameters are updated, and then quantum circuit runs again, and this process goes on and on for some time until you converge, the objective function converges to a suitable value. Okay, so that's what, and these are like called the layers of quantum approximate optimization algorithm. So there's a 1 layer, 2 layer, and as many layer as you can add, the results will converge faster. But at the same time, you have to be careful, because since these quantum hardware are very noisy, the more layer you add, there is more error you are accumulating. So there is a fine balance between, at least for these kind of devices, NISQ devices, there is a fine balance between number of layers you can add to avoid noise and get like the best accuracy of your results. Okay. So we can now just go to hands-on lab. So basically what we'll do in hands-on lab is that we'll design a quantum circuit like this, which will have some free parameters, and we'll run a training training pipeline in which we will try to optimize these parameters to in such a way that the objective function becomes minimum. All right, so let's do that. And for that, if we go to the very first web page up here, the workshop studio, in there there is this thing called QAOA with Penny Lane and Amazon bracket hybrid jobs. You click on there, right? And then there is like download this zip file, QAOA _Penny Lane _ hybrid jobs. You click on that and you save it somewhere on your laptop. And you can just drag and drop that zip file to the a Jupyter Lab up here, and you've got it here. And you will need to unzip that file. If you double click, it doesn't work. So you can go to terminal to ls, and we see that this zip file already shows up here, QAOA underscore PennyLane. So we do this unzip QAOA minus e, let's call it. Oh. I'll unpack this in this directory up here. If you refresh, there is this directory, QA underscore PennyLane underscore hybrid job. Are you able to do this so far? Rob, are you able to follow everyone? How about on Zoom? Are you guys with me?
Can you go back to the beginning of the folder? Is that under examples or the? Oh, no, I'm sorry, I'm there.
Oh, you can save it anywhere you like. I mean, you can, yeah. So let me start it again. Okay. First, you go to the Workshop Studio folder, like a web page, and you download this zip file. In the first step, download this zip file, QAOA underscore PennyLane. When you download that, it is saved on your laptop somewhere. Now you go to Jupyter Lab. You can go to the home directory up here and drag this zip file up until this. Okay. And go to the home directory. And you need to change directory to SageMaker, cd SageMaker list. Now you will see that there is bracket algorithms, bracket examples. There's a folder here, and then there is a zip file, QAOA PennyLane hybrid jobs. Now you need to unzip that file. Unzip QAOA -t QAOA zip. When you do that, it will create a directory here, QAOA underscore PennyLane hybrid jobs. So far, so good?
Yep.
Okay. You go to this folder, and now you have this Python notebook. Double click on that, it will open up here. And this says solving max cut problem with QAOA PennyLane. Okay. So first, some basic imports, basically. Now problem setup. So in problem setup, what we are trying to do is we are setting up a graph. We just created this graph, right, with 5 edges, and we want to find out what is going to be the maximum cut solution to this. And as it turns out, there are many maximum solution to this problem. So there are 5 vertices. So what we'll be doing is like we'll be creating a 5-qubit circuit, parameterized circuit, in such a way that at the end, what we want is we want a separation, like in such a way, like for example, a 5-qubit string of ones and zeros, indicating the separation of these vertices into 2 subsets, right? For example, 0, 1, 2, 3, 4. So if 1 and 2 are in one subset, and 0, 3, and 4 on a different subset, then we would be expecting a string something like 0, 1, 1, 0, 0. So that will correspond to this kind of partition where 1 and 2 are in subset 1, and 0, 3, and 4 are in subset 0. Okay, so in this hybrid job, we are going to find out what are those possibilities which correspond to this kind of max cut solution. Okay, so to prepare the input data, so input data is basically the graph itself. This is an input data. So input file path, if we run this, there's an input data list that is created here. Basically, this encodes the graph. The graph is our input. Now we look at the algorithm script. So let's dive a little bit deeper into algorithm script. Algorithm script is under this QAOA, and there are two files here. One is utility functions, and other is algorithm script. If you double click on algorithm script, what you have here is like some basic imports. Then there is the main program. It says an input directory that is given by some environment variable. Output directory is set by the environment variable, and so on and so forth. So you can give all this as like hyperparameter from the job itself that I will be showing you in a minute. Then like there are some more like seed for random number generation. The parameter P, basically that corresponds to the number of layers in a QAOA circuit, how many shots you want, what is the step size you want, like number of iterations you want. And then there's an interface, which I will talk about in a second. And then basically what we are doing is that this QAOA layer is a parameterized circuit for quantum approximate automation algorithm, and then you build the circuit. So with the help of these two functions, you are building a quantum circuit, and then you are running that quantum circuit on some device up here, and at the end computing the expectation value of the Hamiltonian, and that becomes the objective function, and it runs. Okay, then we can further define some checkpoints in the hybrid job, but I think like in the interest of time, let me go forward and talk about log metrics. So these log metrics are quite interesting, and then you can as the code progresses in different iterations, you can monitor the value of the cost function in real time, and that we will be doing. That will be doing soon when we run this job. You can save the checkpoint data. Like for example, if the job is stopped for some reason, maybe you are running on a quantum hardware, and that hardware is not available for some time. After some time, then this checkpoint is saved, and you can just restart your job at a later time where you left off, and then it can run up here. So this is this script. So basically, script is the meat of all the quantum tasks. That basically it defines what one is going to do when we access the quantum computer. Now, if we go back to the notebook up here, now so there is some basic imports, and then I was talking about the interface. So the interface is like there are three types of interfaces already defined. One is the default one, the AutoGrad, that has penny lane in it. Then there is a TensorFlow interface, and there is a PyTorch interface. So you can use either of these three for your job, depending on what you need. But let's say you need something else, some other packages to be added to these, then you can create your custom interface, and that can be, uploaded and as a container, and all you need to do is just provide this image URI here to be used there. So that container is basically just a collection of packages that you are interested in, or that your algorithm requires. So here we'll be using AutoGrad, the default one, where penny lane, and then we do this. Now we configure. So we define interface as AutoGrad, which is the penny lane, and then we tell the hyperparameters. Like for example, we want to run like 2 layers, the random seed, the number of iterations 20, maximum parallel 10, step size 0.1, shorts equal to 1000, and interface is autograph basically. And we want to use the state vector 1 device for this simulator, and select container. So when we do select container, it loads this interface that we have selected, that autograd, to run. We run this cell by shift enter, and this is all defined. Now we submit the bracket task. So bracket job, hybrid job. So AWS Quantum Create, what we're doing to do is like, we're asking it to be run on a certain device, and that device we have selected up here as state vector 1. Source module is QAOA, like there is this folder called QAOA, that is what the source module is. Entry point is QAOA algorithm script. So QAOA dot means under folder QAOA, there's a file called QAOA algorithm script. That will be where the script is basically. So that'll be the entry point. Then image URI is the basically the container image that we have just selected up here. Hyperparameters is hyperparameters, and the input data we had just created here. So that's that. And then there is some name of the job that we can get. So in this cell, what we have done is we have curated all the information about what the quantum circuit is going to be. That's this circuit. What the device is going to be, that's state vector 1. And what the hyperparameters are going to be, that we have just defined up here. And this algorithm script also contains like the, if you go back to the algorithm script, it has this, optimizers. So that, if, for example, interface.get SGD optimizer. So this is the classical part of optimization. That it is pulling up from penny lane and optimization is starting. So we have defined our algorithm script, basically classical and quantum part, and we provide that to this job, and we submit this by shift enter. So it takes, and this job has been created now. Now we go back to the Amazon Bracket console. But before I do that, are there any questions?
I'm having trouble following it. It seems like we kind of leaned over into neural network.
Yeah, so this is like neural network. So instead of having neural network, so in a neural network, what we have is that there are a certain number of free weights, and in each iteration, we are trying to optimize over those free weights. So instead of neural network, we designed a quantum circuit. And in quantum circuit, these gates, quantum gates, rotation gates, have free parameters.
Okay, so I see the correspondence.
Right. So this parameterized quantum circuit acts very much like a neural network.
Okay.
You can go as far as calling it a quantum neural network even.
And if you race them under their conditions, the idea is that the quantum would resolve faster.
Yes, I mean that would be the idea. Like if you're running for max-cut problem, for example, those Hamiltonians are hard to simulate on classical computers.
Mm-hmm.
So for a large enough problem, I mean, the quantum computer should win over the classical.
Okay, I feel caught up.
Yeah. Okay, so now let's check the status of this job. So we go to hybrid jobs, and somebody else in my team has also created, but let me see which one is mine. So if I do job state, it's running. Oh, this is job result. Start time. Job dot. Oh, sorry. I think let's try this one. This was I think mine. Click on this one. The runtime has been 9-7. That doesn't sound like mine. Yeah, I think this is what I submitted. Okay, so if you see up here, like there is a list of hyperparameters that we submitted with, like p equal to 2, seed, max parallel, and so on and so forth. The input graph is saved up here, and output data configuration is in this S3 bucket that results are stored. What I want to show you here is view in CloudWatch. So CloudWatch is a service where you can like monitor everything, how it progresses. And up here, this is the job. Yeah, so on this, all right. Oh, metric filters. Yeah, so it takes some time for you know, the metrics to upload. In the meantime, let's go back to up here. Yeah, so in okay. So if you go back to CloudWatch once again, yeah, and click on this log stream. So this has the entire, yeah, so it was there. I was just looking at it. So this has the entire log, like when the job started, it like started some training toolkits up here, some like metadata, like output directory, channels, and all that. And if you go further, like it loaded the value of hyperparameters p equal to 2, seed, shorts, and everything. Then it, all the log, basically beginning step, setup, initial cost function is -3 point and all. The iteration number 0, this is completed iteration number 1, 2, 3, 4, and now it's progressing. So if you click on resume, it will give you the most updated, information up here. Okay. Now if you go back here on this job, hybrid jobs itself, there's events. So events, it basically tells you about starting instance, downloading data, then monitor. So in monitor, basically you see that bracket task cost. So as the iteration number increases, on 0th iteration, the cost will be like 16 cent. And second iteration, it increases, fourth iteration, and so on and so forth. So basically, it's just telling you the cost of computing in terms of dollars. And then, so there's a cost, bracket cost, and this is cost. This cost is cost function. It's not the same as bracket cost. This is like objective function. And if you refresh this monitor, so this is still working. It takes like 7 to 8 minutes to completely converge, right? So this is an objective function. It is running. Yeah. So, and we are just waiting for it to be completed. Okay, it's flattening. We can go to hybrid jobs. Okay, so this job is completed. Somebody submitted that. Let me just go to this job and do the monitor. And it's doing some weird things up here. So it did not converge properly, I suppose. we'll need to play with the hyperparameters up there, maybe. Yeah. So this one took 9 minutes, and for this one we are still at 6 minutes 30 seconds. So for a couple of minutes more, we can wait until this job completes, and then I can show you how what the results look like. In the meantime, are there any questions? So there's a question like, does CloudWatch automatically kick in? Yes, it automatically kicks in for hybrid jobs. There is always the CloudWatch is provisioned by default. You can always, whenever you go on the web, like this dashboard of hybrid job, there will be always a link view in CloudWatch. So whatever metric you have defined, you will be able to see that up here, and in CloudWatch, the real-time progress.
Point out, you might want to repeat what I'm saying to the online people, because I'm sure they can't hear me.
Yeah.
But I found this really cool thing under bracket algorithms. There's a textbook that has quantum Fourier transform and all kinds of other notebooks that look really interesting.
Yeah, so in what Rob is saying, that like, if you go to the home folder here in bracket algorithms, go to textbook, and in textbook there are many kinds of different algorithms available up here. For example, quantum Fourier transform, phase estimation, quantum walk, Bernstein-Vazirani algorithm. All the notebooks are available there for you to explore. You have like next 66 hours or so to explore that in the meantime.
So quick question, if we want to start exploring this, there's a lot of material. Do you have like a list of things that you can recommend to go in some kind of order when going through the notebooks and examples?
That's a good question. Like, so, I mean, in bracket examples, you can go and you can start with getting started, basically. So getting started has like what we discussed today, simulation with simulators, QPU device, and then a deeper dive into anatomy of quantum circuits. Then you can look at hybrid jobs, and you can go to hybrid quantum algorithms, which has like a QAOA algorithm, right? And then in bracket examples, you have penny lane. So how you can parallelize quantum optimization of quantum circuit with penny lane, and graph optimization with QAOA. There is, yeah. And if you're interested in looking at bracket features, different kind of features, as in like, so this is like a deeper dive into it. But I would recommend to first start, familiarizing yourself with getting started folder. They'll like, especially the first 3. So try to run it like, and convince yourself that you understand this. And then,
is this all just like a public GitHub repo that I could copy?
Yeah, you can. So this like example is available already in Amazon bracket. GitHub. Bracket examples. Inside this examples, like getting started, hybrid job, it's all there. You can clone it. But if you want to run it on your local laptop, you'll have to install Amazon bracket SDK. Yeah. But if you want to use any managed simulators or devices, for instance, you will need to have AWS account.
Mm-hmm.
And this account will be active for next 72 hours. So you can just directly do that. And
right, but if I wanted to keep going after 72 hours,
yeah,
it doesn't look like I'd be paying a lot of money to be playing with this stuff.
Yeah. I mean, that won't be too much, unless you
make a mistake.
start running something. So if you provision a notebook, as we discussed this today, through AWS account, then you don't need to clone that directory. That bracket example and bracket algorithm, they're already by default there. These first 2 folders are already there. Let's check on this job. It seems that this job has completed. So now we can retrieve the result. And when we retrieve the result, it looks something like this. Can do task summary that the estimated cost to run this job was like $3. And let's investigate this result. So now these are the final optimized parameters. So apparently we had like 2 layers, and each layer there were 2 parameters, right? So it's called alpha 1, beta 1, and alpha 2, beta 2. So these are the final values of the parameters that we're looking at. I mean, and in any machine learning algorithm, when you train a neural network, at the end, as a result you get is the number of like value of all the weights. This is similar to that, right? And then if you want to look at the result, I mean, this is the copy of the you know, the algorithm script basically. And what you want to do now is like with these optimized parameters, you want to see what the final result is going to be, because this is just the optimized parameter. It doesn't tell me what the max cut is looking like, right? So for that, we'll just create the circuit once again, and we'll run this circuit with these parameters like 1,000 number of times, like 10,000 number of times, or 100,000 number of times, to collect statistics to see which are the most likely outcomes. So we run this. It ran now. So it turns out like partition of all, like, remember we had a graph with 5 vertices, right? So we are just looking for a bit string with highest probability. Okay, so these are the bit string we have. There are 32 possibilities of this 5. So all zeros means there is no cut. All of these vertices being in the same subset, probability of that is 0.01. Now in this, we see that there is this possibility. Oh, sorry, this possibility has 0.1, and the other possibility, this has 0.1. And if we plot this, it looks like, so 1, 2, 3, 4. There are 4 outcomes which have high enough probabilities. Let's plot these four outcomes and see what they look like actually. So if we do that, so list bit string 11100, like this being in one group, and 3 and 4 being in one group. So that will correspond to a cut like this. I cut this edge, this edge, this edge, this edge, and this edge. So how many cuts we made? 1, 2, 3, 4, 5. So we made 5 cuts. So, and in this graph, if you like analyze, 5 is the maximum cut you can have. But there are more solutions possible, right? Because there is a symmetry in this graph. So the other possibility is like this. We have 1 and 2 in this group. And what one is trying to do now is, how this cut is going to be, is something like this. You cut this edge, this edge, this edge, this edge, this edge, and this edge, like this. So that will be 6 cuts, I think. Yeah. No, sorry. Yeah, this cut like this. This edge, this edge, this one, and this one. That is also 5 cuts. This, 2, 3, 4, and 5, and it separates the vertices into two parts, where these are in one group and these 2 are in the other group. Yeah. Then there is another, and this solution is very much similar to this solution. It's just on different vertices. And here again, this is actually, this solution is just complement of this solution, second solution. And then similarly up here. So we got like 4 high probability solutions. They are all a max cut. and the number of edges cut is 5. I printed out another, the 5th possibility, that is not actually a max cut. And as you can see, like this is just cutting the graph like this, where second vertex is in one group and the rest all are in another group, and the cut is only 2, and the probability of this is like 0.04. So indeed, the higher probabilities, probability outcomes do give you the max cut that you're looking for. So yeah, so that's the result I wanted to show you.